Hi, Calc students. We're going to continue our work with integration by substitution or use substitution. And we're going to look at some other integration techniques. So I'm going to share a presentation with you. I believe the first slide is a warm-up. So you might want to grab a piece of paper and a pencil and try the warm-up before we get started on the presentation itself. So go ahead and pause and try these two practice problems. We'll warm up. All right, welcome back. Let me grab my pen. Let's see how you did here. I'm going to go with blue. So evaluating a definite integral, remember our process is to find the antiderivative of all the parts and evaluate it at the limits of integration. So antiderivative of x squared is 1/3 x cubed. Antiderivative of x would be -1/2 x squared. And we are evaluating that from 1 to 5. So first I put a 5 in everywhere. So 1/3 times 125, I'll have 125/3 minus 5 squared is 25, 25 halves. Minus, and next I'm evaluating with 1. So 1 cubed is 1. We have a 1/3 minus 1/2. All right, I'll keep simplifying. 125/3 minus 1/3 is 124/3. And then we have -25 halves plus 1/2 would be -24 halves. And let's see, that looks like, does that go in there? Probably not. So that's a 12. So we have 124/3 minus 12. I bet I walked down here without a calculator. I did. So I'll let you guys do the simplifying here. Looks like 124/3 minus 36/3. And I'll let you guys do that subtraction. All right, the second one, not a definite integral this time. So I'm going to first rewrite this. I'm going to distribute secant. So that gives me secant squared x plus sec x tan x. And hopefully you recognize these from your integration techniques. All right, so antiderivative of secant squared is tangent x. Antiderivative of sec x tan x is secant x. And remember, when there aren't any limits of integration, when it's an indefinite integral, I have to remember to put plus c in here. All right, let's go ahead and continue with the presentation. We talked about doing substitution, and I mentioned that quite often. If you can recognize the pattern, you don't need to go through the whole use substitution process. So it says here, the integrand of each of the following integrals fits the pattern f of g of x times g prime of x. Identify the pattern and use the result to evaluate the integral. So if I look here, I'm really looking at this complicated part. So if I looked at this and I found the derivative, if I use the chain rule, the derivative of this g of x here, g prime of x would be 2x, and there it is. So then I really just need to find the antiderivative of x squared plus 1 to the 4th, which would be 1/5 x squared plus 1 to the 5th, right? Once I recognize the pattern, I don't need to worry about the chain anymore. I can just look at what was the function, find its antiderivative. All right, here's another case. We have x cubed plus 1. If I find the derivative of x cubed plus 1, I'd get 3x squared, which there it is. Derivative of 1 is 0. So I'm really just looking at this. This would be x cubed plus 1 to the 1/2. Antiderivative would be 2/3 x cubed plus 1 to the 3/2. The chain rule is taken care of when we deal with the inside part. All right, here's another one. So it looks like here's my more complicated part. Derivative of tangent is secant squared. So I would be finding the antiderivative of tangent of x plus 3 to the 1st. which would be 1/2 times the tangent of x plus 3 squared. All right. It says the next three integrals are similar to the first three. Show how you can multiply and divide by a constant. So we did some of these yesterday. My derivative here of the inside should be 2x. I don't have a 2x. If I put a 2 in, I would need to take a 1/2 outside the integral before I found the antiderivative. Right, the next one, similar to this one up here. Notice we don't have the 3x squared here. We need it. If we put the 3x squared in, I need to take a 1/3 outside. All right, our last one, derivative of tangent is secant squared. I have it, but I also have some extra information. When you have a constant inside, it can go outside. So I would just have a 2 outside the integral, and I would go ahead and find the antiderivative of tangent of x plus 3, which we did up here. All right, so that's the general idea of what we're doing today. So let's look at some. All right, so this first example, I'm going to grab my pen. This first example, we want to recognize the patterns. Let's see, I go to this more complicated part here. Derivative of 5 is 0. Derivative of 2x cubed would be 6x squared, and there it is. So it's really just this part here that I need to find the antiderivative of. This is 5 plus 2x cubed to the 1/2 power. So the antiderivative using the general power rule, 1/2 plus 2/2 would be 3/2. So I'd end up with 2/3 times 5 plus 2x cubed to the 3/2 plus c. Okay, notice I could have done the use substitution technique we were doing in class yesterday, but this just saves me a little bit of work if I can recognize that pattern and see what should be there for that chain rule part. If you're not sure if you've done it right, take the derivative, use the chain rule, see if you get back to what you started with. All right, let's look at B. Now, one thing on B, anytime you see a fraction, the first thing you should suspect is that perhaps it's an ln problem, because remember, the antiderivative of 1 over x dx is the natural log of the absolute value of x plus c. So anytime you see a fraction, you should think, is this an ln problem? We use the absolute value because if we recall, if I look at the graph of the natural log of x, there's a vertical asymptote at 0. It has a 0 at 1. The natural log function goes like this. So that's kind of, I made it look really square, but it's curved more. So it's only defined for values of x that are greater than 0. So we need to make sure we have this absolute value. So we're only getting positive values for our ln. All right, so I'm going to look at that. So I'm thinking, is this an ln problem? Well, let's look at if it is, we'd have to have some chain rule. So what's the derivative of x cubed plus x? It would be 3x squared plus 1. So this is, in fact, an ln problem. So I would get the antiderivative is the natural log of x cubed plus x plus c. All right, again, if I were taking the derivative, I'm just going to do a little aside here to make sure we're right. I'm even going to switch my pen color just to see that this does work. Remember with ln, our first process, if I'm taking the derivative, if I want to take the derivative of this, I would first do 1 over x cubed plus x. Then I'd have to do the chain. Derivative of x cubed plus x would be 3x squared plus 1. So I would end up with 3x squared plus 1 over x cubed plus x, and that's what I started with. All right, so this answer that I got here is, in fact, the antiderivative. All right, that's my solution to B. All right, let's look at this one. Well, let's see, we have sine 3x minus 1. Chain rule says there should be, if I take the derivative of 3x minus 1, I get a 3, so this is correct. So now I need to find the antiderivative of sine, which should be negative cosine of 3x minus 1 plus c. All right, again, you can always double check. Are you right? Derivative of cosine is sine. Excuse me, derivative of cosine is negative sine. That's going to make it positive. Derivative of this inside part would be 3. And there it is. All right, so we did it right. All right, sometimes you have to multiply or divide by a constant. We looked at some of those, like it looks like the original, except that it's missing a constant. So here's my complicated part. If I take the derivative of this inside, I should get 3x squared, but I don't have my 3. So if I put my 3 in, I've got to grab a pen here. If I put my 3 in, I need to take a 1/3 out. Now I've taken care of the change, so I'm really just looking at this part here and finding the antiderivative of that. So I still have my 1/3. And notice all of these could have used use substitution. I'm just showing how you could do it without it. So I'm really finding what's the antiderivative of something to the 4th power. Well, that would be to the 5th power, right? General power rule. I need a 1/5 times whatever it is that I'm taking the antiderivative of. 4 plus 1 is 5. And again, 5 times a 5th is 1. Reduce this power by 1 and we'd be at 4 plus c. And then we're going to just clean that up. 1/3 times 1/5 is 1/15. X cubed plus 5 to the 5th power plus c. All right, let's see this one. Well, there's certainly this secant squared 5x, but if the chain rule had been done correctly, there should be a 5 in here, and we don't have a 5. So I'm going to put my 1/5. If I put my 5 out here or in here, I need a 1/5 on the outside. So now I have 1/5 times antiderivative of secant squared is tangent. So we should have the tangent of 5x plus c. Again, if you're not sure, take the derivative. Derivative of tangent is secant squared 5x. Derivative of 5x is 5. That 5 would cancel with 1/5, and we'd be back to what we started with. All right, this example was done in your notes. I'm not going to go through it. You should be able to walk through step by step, change of variables. This is the use substitution that we did in class yesterday, where we rewrote, we found a u, found a du, rewrote our integral in terms of u, and then found our antiderivative, and then substituted back. So we're going to try some of these with the change of variable or use substitution. On example 4a, you actually have, they're very similar. It doesn't matter which one you choose for u. I think I chose u was equal to, what did I pick here? I did sine 2x. But these are so close and their derivatives are so close and their antiderivatives are so close. It doesn't matter in this case which one you pick. You always try to kind of pick the more complicated one if you look in your notes. So I have u is equal to sine 2x. So the derivative of that, derivative of sine is cosine 2x. But then with the chain rule, the derivative of 2x is 2. So if I look, I have everything I need except for the 2. So again, if I put the 2 in, I need to take a 1/2 outside. So this integral now is going to turn into 1/2. And again, remember, we're doing the change of variables. So our du is this whole cosine 2x dx with the 2. All right, so all of that is my du. And my u is sine of 2x. So we have u du. All right, antiderivative of u would be 1/2 u squared. So I have 1/2 times 1/2 u squared. All right, plus c, or 1/4 u squared plus c. And then just remember, when you do this change of variables, you need to change back unless it's a definite integral. This is an indefinite integral, so I need to substitute back for my u. So I end up with 1/4 sine of 2x squared, which usually you'll see when sine is squared, they put the squared in the middle. So sine of 2x plus c. And again, remember, you can check your work by taking the derivatives, right? All right, this time we have the antiderivative, or the integral of tangent x. Now you may have wondered, why hasn't this come up before? Well, let's talk about why it hasn't. And the reason is because you hadn't had this use substitution technique before. So I'm going to rewrite this as sine x or cosine x, or I should say you haven't had the chain rule with derivatives yet. So I'm going to rewrite tangent as sine over cosine. And now you can kind of see, oh, I have a fractions, so I should suspect that perhaps this is an ln problem. All right, so I'm going to let u equal the cosine of x. Then my du would be equal to, derivative of cosine is negative sine x dx. All right, so I know I need a negative in there. If I put a negative in, I take a negative out. So I have a negative. And then this is going to be 1 over u. All right, there's my 1 over cosine. And this whole sine x dx, remember, I've already taken care of the negative. I brought it outside. That's my du. All right, when I have 1 over u, that's an ln. So I have a negative absolute value of u plus c. All right, last step is to substitute back for my u. So I have the absolute value of cosine of x plus c. So you will look, if you look in the inside cover of your calc book, you'll see all these other trig integrals that we hadn't had yet because we hadn't had use substitution. We hadn't had the chain rule with derivatives yet. So this is negative ln, absolute value of cosine x plus c is the antiderivative of tangent of x, right? This turns into this. All right, let's look at some others. This time we have one where we need to remember how to change the limits of integration. We did a few of these yesterday in class. So let's see here, our u in this case looks like it's 1 plus x. Our du would be equal to derivative of 1 plus x is dx. Right, so this one's not so bad. It's the integral of 1 over the square root of u du, but remember we have to change our limits of integration. So when x equals 0, right, that's our lower limit of integration, 0, u is going to be equal to 1 plus 0 is 1. When x is equal to 3, that's our upper limit of integration here. Our u is equal to 1 plus 3 is 4. So this integral turns into the integral from 1 to 4, new limits of integration, 1 over the square root of u du. I'm going to write that as the integral from 1 to 4 of u to the negative 1/2 du. I find the antiderivative, and remember when it's a definite integral, when you're finding the antiderivative, you can do it, evaluate it at these values. You don't have to change back to this 1 plus x. So antiderivative of u to the negative 1/2, negative 1/2 plus 2/2 is 1/2 over 1/2 would be 2 u to the 1/2, positive 1/2, evaluated from 1 to 4, or if you'd rather think about it with square roots, this 2 times the square root of u, evaluated from 1 to 4. So first I put my 4 in there. So I have 2 times the square root of 4 minus 2 times the square root of 1. Square root of 4 is 2, 2 times 2 is 4, minus square root of 1 is 1, 1 times 2 is 2, and 4 minus 2 is 2. All right, we're also going to take a look at some inverse trig integrals. So if we look, these are in your notes here. Recall that we have arcsine, arctan. Sometimes arcsecant comes up, sometimes arccosine. The ones you're going to see the most, if you see them at all, will be the arcsine and the arctan. So if you have one like this, remember our first thing was to go, oh, is this a possible ln? Well, this isn't looking like an ln problem, because if I take the derivative of x squared minus 4x, I get 2x minus 4. There's no way I'm getting a 2x minus 4 out of that. So then I have to think, okay, this isn't an ln problem. There isn't really anything else I can do. Is this possible that it's an inverse trig? Well, in this case, I don't have a square root, so I have to rule out that it's arcsine, and I have to think it's possibly arctan. So kind of to a little aside here, I'm thinking arctan question mark. All right. That's what I'm wondering. And remember arctangent, if I have, well, if I have an integral of, let's see, they wrote it as du equals a squared plus u squared. That antiderivative is equal to 1 over a arctan u over a plus c. Remember, arctan is the same thing as tan to the minus 1. All right, so I'm wondering if it can possibly be this. Well, I don't really have something squared plus something squared. So the question is, can I rewrite this somehow and get it to look like the sum of two squares? So we're going way back to algebra 2 today. We are going to be working with, and the other thing I'm going to do is I'm going to take this 3 outside here. It's kind of in my way. It doesn't have really anything to do with the problem. So I am going to make this be the sum of two squares by completing the square. So I'm going to leave some space here, and I'm going to put my plus 9 back in. All right. I'm going to switch colors here for a second. So completing the square, remember this is your middle term, your b term. You take half of that. So half of 4 is 2, and 2 squared is 4. And I add 4. But I can't just add a new thing on the denominator without doing something to counteract it. So I'm going to subtract 4 out here and extend this. So now I'm going to rewrite it. I'm going back to my blue. This now turns into 3 times the integral of 1 over. I've completed the square here, so I can now write this as the square of a binomial, x minus 2 quantity squared, right? That's what this is when I factor it. And here, remember, we counteracted that plus 4 by subtracting 4 outside, and 9 minus 4 is 5. All right, so it's close to looking like an arctan integral here. I'm going to switch things around because our a is the value that's the constant, and our x minus 2 is going to be our u value. All right, so our u is equal to x minus 2. Our du is equal to dx, right? Derivative of x is 1 dx. Our a squared, right? It's in this spot. We have something squared plus something squared. So our a squared is being represented by the 5. So that means our a is the square root of 5. All right, so now I'm going to find my antiderivative of this. If you want to put this in terms of your u and your a, you can. All right, so I'm going to rewrite this as, and I'm going to go ahead and put it with the u's. So this turns into 3 times 1 over, our 5 is a squared plus u squared. So our antiderivative then is going to be, and I've got this 3 that's going to get carried through. I'm going to have 3, right? I'm going by this, 3 over a, which is the square root of 5, times the arctangent. Then we put in our u, and our u is x minus 2. Over our a again, right? There's our a. Our a is the square root of 5 plus c. All right. Don't worry if that you got bogged down by that one. The likelihood of one of these where you have to complete the square isn't very likely. It might be in a multiple choice, but it'd be pretty unusual to see it there. All right, let's look at example 7. Now this time, one like this could come up. Again, we have a fraction. Our thought process is, I'll find my pen here. Is this a possible ln? Well, let's look. We have, if I make u equal to 1 plus e to the 2x, right? Because I'm thinking this is possible ln. Our du would be equal to, derivative of 1 is 0. Derivative of e to the 2x would be equal to 2e to the 2x. All right, so it's possible it's an ln. I might want to throw a 2 in here, right? The problem is I can't invent this 2x as an exponent, all right? So I have to realize that it's not an ln problem. All right, so now remember the other kind we have where it's a fraction and a plus something in the denominator, again, is our arctan. So I might be thinking, is this an arctan problem? Right? Well, let's see. Remember arctan, we need to have a 1 over a squared plus u squared. And our du. All right, so, and they have du on top. Well, let's see, can we square something to get 1? Yes, our a could certainly be equal to 1. But now the question is this something squared? Well, let's look. We have our e to the x. This is 1 plus, and yes, I can write this as e to the x squared. All right, remember properties of exponent, if one's on the inside and one's on the outside. So this is in fact e to the x squared. So our u is equal to e to the x. Then if I do my du, derivative of e to the x is e to the x. And so this whole part of the problem turns into our du. And this turns into 1 over a squared plus u squared du. So the antiderivative of that comes out to be nicely the arctan. And I could do my 1 over a here, but our a is 1. So 1 over 1 arctan. And then we have u over a, so e to the x over 1 plus c, or just the arctan of e to the x plus c. All right, could there be one like that on the AP exam? Yes, I'd say that's pretty likely, right? That's not a very far stretch to get to that one. All right, so I hope looking at these other techniques helped you. Your assignment is at AP Classroom. Whoa, wait, we have one more problem. I thought that was the end, sorry. Yes, your assignment's at AP Classroom, but let's look at this first. All right, so fraction time. So fraction, is it an ln? Oh, I doubt it. What's the derivative of 3x minus 1? It'd be 3. I'm certainly not going to get that. So it's not an ln. I'll grab my pen here. Uh-oh. I gotta go all the way to the end here. Whee! Didn't mean to hit that. I meant to hit my pen. All right, let's do that again. All right, it's not ln, because there's no way I can take the derivative of 3x minus 1 and get this. All right, is it a possible trig? Well, let's look. Is this something, arc cos, arctan? Doesn't look like it. This isn't anything squared. I guess that's a 1 squared, but remember arctan has a plus there. And there's no way I'm going to get a nice derivative out of this. So now what? So I'm going to say it's not ln. It's not arctan. What do we do? Well, when you have one like this, you can divide and rewrite the integral. So I'm going to do long division here. I'm going to divide 3x minus 1 into 3x squared plus 5x plus 3. All righty. Review time. What do I multiply 3x by to get 3x squared? I'd need an x. I multiply back. X times 3x is 3x squared. X times -1 is -x. Remember the division algorithm. The next step in division, once you multiply, is to subtract. So this turns into a minus. This turns into a plus. Those terms cancel. 5x plus x is 6x. And I bring down my 3. Right? We start the division process again. How many times is 3x going to 6x? Or what do I multiply 3x by to get 6x? I need a 2. So 2 times 3x is 6x. 2 times -1 is -2. The next step is to subtract. So that's going to make this negative and this positive. The 6x's are going to cancel. 3 plus 2 is 5. I cannot multiply 3x by something and get a 5, so that's my remainder. And I'm going to write it as 5 over my divisor, which is 3x minus 1. So this quotient here represents this integral. So I'm going to rewrite this integral now as x plus 2 plus 5 over 3x minus 1 dx. All right. I should be able to find the antiderivatives of all of those things. So if I look, antiderivative of x is 1/2 x squared. The antiderivative of 2 is 2x. And this time, yes, I can look at this as an ln problem. So I'm going to change pens here for a second, switch colors. I'm going to do like a little aside problem here. I'm going to turn this into 5 times the integral, that's an integral sign, 1 over 3x minus 1 dx. All right, I think it's an ln problem. My u would be 3x minus 1. My du then would be 3. So I need to put a 3 in here. If I put a 3 in, I need to take a 1/3 out, which is going to turn this into 5 over 3. So now I'd have 5/3. And this would in fact be, antiderivative of that would be ln absolute value of 3x minus 1. All right, so let's go back to our original problem. This whole part here now is going to turn into 5/3 times the natural log, absolute value, 3x minus 1 plus c. All right, that's an ln, by the way, and that's a 5. Okay. So that should be the last slide. And again, the homework assignments at AP Classroom. Hopefully this helped. If you have other questions, you can email me. or ask me during class. All right, good luck.